these are our common limit rules that we see in most textbooks, right? We see the limit of a product of f and g is equal to the limit of f times the limit of g. We often see the limit of a sum of f plus g is equal to the limit of f plus the limit of g. And then we also see the composition, that the limit of the composition f of g is equal to the limit, or f of the limit of g. And these are three basic rules that we've applied. And I think what we've seen in recent years is that students particularly, but I think even myself as a teacher, is I've forgotten to consider and show my own students that all of these rules have conditions, right? That we can't just use these arbitrarily, but we have to first check for conditions. So for example, these first two rules here, both of these work if the limit of f exists and if the limit of g exists. So both of these rules are applicable if these two situations are both true, right? And so what happens is when we get problems nowadays, sometimes we're going to see some questions where those conditions aren't met. And so if the limit of f doesn't exist, or if the limit of g doesn't exist, or even if both don't exist, it doesn't mean that the limit of the product doesn't exist. It simply means that we cannot apply this rule. I think sometimes what we do is we take this conditional statement and we end up making it a biconditional, right? And so what happens is, if the limit of f exists and the limit of g exists, then the limit of the product and the limit of the sum are given by these two rules. If one of those conditions fails, or if both of those fail, it only means that we can't use those definitions. So what do we do, right? So what do we do when one of these limits doesn't exist? How do we approach these problems? Well, I think the best solution to tell our kids is, what do we do from the very beginning? When we first teach our kids limits, if we're using graphs or tables, we always go back to say the limit of any function is going to be equal to a number if the limit from the left of that function equals the limit from the right side of that function. And if those two limits from the left and the right are the same, then the overall limit exists, right? So if we see a product of two functions or a sum of two functions, and one of those functions doesn't have its own individual limit, it doesn't mean that the whole limit doesn't exist. It just means we can't use this rule. We have to examine the left and the right. I think one of the things that students have a hard time with is they end up looking at these functions here, and they see these as f and g, but really this whole thing represents a new function, right? It's a new function, h of x. So I'm not technically asking about f here, and I'm not technically asking about g here. I'm asking about the sum of f and g, which is created by a third function, which we'll call h of x. If I want to examine h of x, I really should examine it from the left and from the right. And we'll see a couple of examples here in a second of how this might look in our classrooms. I think the third rule we use a lot is this composition function, right? The limit of f of g of x equals f of the limit of g of x. This is only applicable if the function f is continuous at this value, right? So when we take the limit of the inner function of g, we can only apply this property if the function f is continuous at that value, right? And so a lot of times what we're going to see is a function where this outer limit f is not continuous at whatever this limit of g of x is. And so again, if we're going to look at this, we really have to consider the left and right side limits. We can't simply just try to say, well, if f is not continuous, then the whole thing has no limit. So the first example I want to kind of jump into is this third example here, and it's going to be one of these compositions problems. And so I've got this this function f here, and I created it on GeoGebra. It looks like, just so you know, it's a couple of parabolas here, and then we've got an open circle at 2, and then we have a line segment that starts up at 2 and goes down to 6. And so I want to figure out what is the limit of f of x. Well, our first intuition would be if we tried to find the limit of the inner function, right? f of -2, if I wanted to look at what is the limit as x approaches -2 of f of x? Well, on this graph, we can clearly see the limit at -2 is going to be 2, right? And so that's the value that we're trying to input into f. But in order to use that rule of doing f of 2, that's only applicable if our function is continuous at x equals 2. And we can clearly see here that it's not continuous. And so what happens is we see some students that will just pick wherever the point is, right? Because they're trying to evaluate a point, and they'll say 4. Or we'll see some students that will say does not exist because at 2, that value that we're inputting in there, there's a jump, right? But really what we should be thinking about here is evaluating this from the left and from the right. And so if I think about this function, as x approaches -2 from the left, and if I think about the limit as x approaches -2 from the right, of course, at this value, they're both going to be approaching 2, right? But I'm going to put this little negative sign on there because they're both approaching 2, but from either direction, if we're following this graph of the inner function, from either direction, as it approaches 2, we're always just underneath 2. So really, what we're importing into the outer function is something that's getting closer and closer to 2, but always just left of 2. And so as we do that, really what we're tracing here then is the left side of this graph, because the values that we're importing in here are going to be like 1.9, 1.99, 1.999, and getting closer and closer to 2, but from the underneath side. So no matter how close we get, no matter what we appear, we're always going to be coming from this side. And so because of that, we're going to end up getting this value right here, which is 2. So because that rule breaks down, because we can't use the f of the limit as x approaches -2 of f of x, we can't apply this property because our outer function is not continuous at this value. And so because of that, we're not looking for a point. We're now having to examine the left and right limits. And so I think one of the things that helps students would be one of two things. One option is create yourself a little table with your kids, and then let's just examine what happens along the way, right? If you want them to be convinced of this, what if we did this, and then we also did the f of x, this composition function, and I want to know what's happening as x gets closer and closer and closer to -2. And so to make that happen, I'll just call this -2 here. And so from one direction, we're going to have like -2.01 or -2.1, and the other side maybe -1.99 and -1.9, and we can create a bigger table if we want to get more values. But notice, no matter what values I plug in, if I plug in -2.1, right, of f of x, that's going to end up being really, really close to 2, but it's about 1.99, very, very close. And when I take that 1.99 and plug it into the outer function of f, 1.99 of f ends up being really, really, really close to 2, right? It's just less than 2. And if I plugged in -2.01, got even closer, now we're like at 1.99 or 1.999, something even closer to 2. But when I plug that in, I'm still going to be over here. So no matter what I'm doing on each of these, we're going to be getting closer and closer to 2. But from any direction we come, from either limit here, if I came from the -1.9 side or the -1.99 side, any of those values are still going to be about 1.9, 1.99, and no matter what value I get, it's still going to put me on this side of the graph. So on either one of these, we're going to end up getting something really close to 2. So as they both approach -2, we're going to see these values are approaching closer and closer to 2. I think what also might help students to kind of believe this is I went ahead and I typed these into my my GeoGebra graph, and then once I was done with that, I decided to graph the composition, and this is the composition. So the composition f of x it has some similarities to our original function, but it is a composition. And so if I were to ask on this graph, what's the limit of f of x as x approaches -2, well, this is the new function. This is not f, this is the composition. Well, clearly, as x approaches -2, from either side, we're going to be approaching 2 from underneath it, right? Which is exactly what we saw when we made a table or if we kind of plotted out those points. So I think one of the things we'll be careful for with compositions is going to be making sure that we don't try to apply those limit properties before we check the conditions, right? A couple more examples here. This is from one of my worksheets or activities that I've made for my own students, is looking at two functions, right? If I have f of x on the left and g of x here on the right, one of the things that the exam might ask our kids to do would be to find the limit of the product, or again, the limit of the composition is another common one. So looking at the limit of the product, what a lot of my students do on first glance is they think this is two separate limits because they're trying to apply that limit rule, right? That property that says this is going to be equal to the limit of f times the limit of g. Like that's what they want to say. And they look at the f function here, and as x approaches 1, the limit does not exist. So then they end up getting, oh, the first limit doesn't exist. The limit of g as x approaches 1 looks to be 1 or 0. So what happens when you take does not exist times 0, and they either panic and choose something, or they say does not exist, or they just kind of give up all hope, right? But I think the bigger error here is, again, they're trying to apply that property that doesn't work, because the property of multiplying their individual limits, you know, right now we have a limit of products, and the property says we can now take the product of limits. That only works if each of those limits exists. If one or both of those limits do not exist, it doesn't give us any indication about what the answer is. It only tells us that we can't use that property. And so in cases like that, what we have to do is go back to our fundamental understanding of limits, which says, let's take the limit of this product from the left. So the limit of f times g from the left, let's examine that limit. And let's examine the limit as x approaches 1 from the right of that same product. And let's see what happens. So if I'm approaching 1 from the left only of f times g, well, in this case, we realize that on the function f coming from the left, we see that our limit is going to be -1. And we see that for g coming from the left of 1, our limit is going to end up being 0. And so our overall limit from the left is going to be simply 0. And if we do the same thing from the right of the product, coming from the right, we realize that the function f coming from the right is going to be approaching 2. And the function g from the right is going to be approaching 0 still. And that's going to end up giving us the product of 0. And so looking at this from the left and from the right, we got the same number. And we know that from our most primitive limit properties, a limit of a function exists if the limit from the left is equal to the limit from the right. And so in this case, we get 0. So even though the limit f did not have a limit as x approaches 1, the product does. The second problem I want to take a look at again is this limit of f of g of x as x approaches 2. And so again, if we're looking at this, if I'm evaluating g of 2 here, it looks like the limit as x approaches 2 of this inner function is 1. And then if I try to take that value and plug it into f of 1, I've got this weird situation where the left is going one direction, the right is going a different direction, and there's a point somewhere else. And so the question is, we can't even apply that property, right? We can't apply that composition property because our function f is not continuous. So we're not able to do that. So what we need to do is evaluate the limit as x approaches 2 of f of g of x from the left, as well as evaluate the limit as x approaches 2 of f of g of x from the right. So we have this left and right sided limits here, right? So if I'm approaching this from the left, looking at the inner function g of x as x approaches 2 from the left, notice our limit is approaching 1, but we're always just less than 1, right? So no matter what, however close we get, the value that we're importing into f is always going to be a value that's just less than 1. So what that means is, as I'm following this graph of f now, I'm approaching 1, I'm getting closer and closer to 1, but I'm coming from the left-hand side. So coming from the left-hand side, we see that our limit there is going to be -1. And then coming from the other side, f of g of x from the right-hand side, we're still approaching 1, but notice even though we're coming from the right-hand side, we're approaching 1 again from just underneath it. So the values that we're approaching are always going to be just slightly less than 1, right? It's going to be a limit of 1, but we're approaching 1 closer and closer from the underside again. So what are we doing? We're following the same path because we're still getting closer and closer to 1, but the values we get will never be 1, and they'll never be more than 1. They're always coming from just underneath it. And so from that direction, we also end up getting -1. So for both of these, we get an answer of -1. So that's another example of having two functions where if you end up taking their product or end up taking their composition, you're going to have to do some more thoughtful discussion on them. And now we're going to look at the limit of f of x plus g of x plus 2. So we actually saw a problem similar to this on the international exam, I think. Maybe it was the practice exam, but in 2017, there was a very similar problem to this, and it kind of asked it in a different kind of way, but it was two functions, and essentially you were adding a sum of them. And so the value we're looking at is that x equals 1. Well, if we look at f of x at 1, we clearly see there's no limit there, right? There's a jump. And then for the other function, g of x plus 2, essentially we're looking at what's happening around g of 3, right? And in g of 3, we see another jump. So here's another example where that property of a sum of limits becomes or a limit of sums becomes the sum of limits. The property doesn't apply, which doesn't mean that there's no limit. It just means that for us to tackle this question, we have to look at this from both sides. So if you haven't really figured this out yet, I think all of these more complex examples, we have to go back to our roots of what really is a limit and when does a limit exist. A limit exists if the limit from the left equals the limit from the right. So whenever students are maybe not feeling very confident about how to answer a question or something seems off, encourage them to break it down to the most fundamental part, which would be examine the limit from the left and examine the limit from the right and see what you get, right? Flavia has a great question. So to be safe, and so here's another example here. So I'm going to approach 1 from the left. Well, looking at f of x from the left, as x approaches 1, we can see that our limit clearly is going to be 3 from the left, even though there's a hole there. And then to this, we're going to be adding the limit on the left as g of 3, essentially, right? So in this case, I just did that backwards. Hopefully nobody noticed that. I'm going to cross this off because I just realized I did this to my students on purpose and I fell for my own trick. I gave them g of x first, right? And then I put f of x on the right. I did that because that way they'll pay attention to it and not just fall into blind problems. And of course I fell for my own rule. So as x approaches 1 of f of x from the left, let's try that. As we approach 1 from the left, f of x is going to be 1, not 3, right? And then for g, as x approaches 1, we get g of 3 from the left. And here we see that the value of that is going to be 4 or 3. And the sum of that ends up being 4. So the overall limit from the left is going to be 4. And then we can do something similar from the right. We can take the limit from the right as well. And so in this case, here from the right of f of x, as x approaches 1, we see that we get 2 in that case. And then again, approaching 1 from the right of this g of x plus 2 function, we're basically approaching g of 3 from the right side. And in this case, from the right-hand side, even though there's a hole in the graph, we're taking a limit, so our limit ends up being 2 as well. And then the sum of those ends up being 4. So notice, even though f did not have a limit at 1, and g of x plus 2 did not have a limit of 1, when we're taking the limit of these sums, we're actually creating a new function. And that new function, if we could see it, had the same limit from the left and from the right. And so we know that our final answer is going to be 4. I love this idea of telling our kids, look, we're giving you F and we're giving you G, but we're really not asking you a question about either one of those, right? We're asking you a question about this mysterious h of x function that you can't see.